The Moselle River, September 1944. The water is cold, running fast after 2 weeks of autumn rain, and 40 feet wide of the crossing point the 3rd Infantry Division has chosen east of Dornat, France. The engineers of the 10th Combat Engineer Battalion arrive at the bank before dawn with rubber assault boats, folded bridging panels, and enough rope and steel cable to span the river twice over. The ground behind them is still smoking from a German artillery barrage. The ground in front of them is covered by German machine guns on the far bank and mortar crews on the high ground above. The engineers are not riflemen. Their tables of organization list them as combat support, men whose job begins after the fight has passed through. That is the official version. What actually happens in the next 6 hours will appear in the after-action reports of 3 different American divisions as the difference between a bridgehead and a disaster. The German 3rd Parachute Division across the water has prepared this bank for exactly this moment. They know the crossing is coming. They know when it is coming. They have registered their mortars on every section of the riverbank where boats can be launched. What they have not calculated, because no German staff officer in September 1944 has yet found a satisfactory answer to the calculation, is what it takes to stop American engineers once the order to build has been given. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. German prisoners taken in Normandy said things about American infantry that showed up in the interrogation logs with strange regularity. They said the artillery was everywhere at once. They said the rifles never stopped. What they said about the engineers was different in register, quieter, and in some ways harder to account for. They said the bridges appeared. The roads appeared. The cratered ground was passable, and then suddenly it was flat. The river was a barrier, and then it was not. Captured officers from the 7th Army, questioned in the autumn of 1944 by 1st U.S. Army G2 interrogators, returned again and again to a word the American translators rendered as unbegreiflich. Incomprehensible. They used it for the artillery. They used it for the radios. They used it, with particular frequency, for the engineers. To understand what they were looking at from the other side of the wire, we have to go back further than the war itself. We have to go back to a philosophy of military construction that the United States Army had been quietly assembling since the closing years of the First World War, when a young officer named Leslie McNair watched the Allied advance stall not against German rifles, but against mud, craters, and rivers that the armies of France, Britain, and the United States could not cross fast enough to exploit what their artillery had won. The German army that crossed into France in May 1940 had its own engineers, and they were good. The crossing of the Meuse at Sedan, executed by pioneer battalions under the eyes of Erwin Rommel's 7th Panzer Division, remains one of the most studied river crossing operations in the literature of military engineering. The German pioneers worked under fire, paddling assault boats, laying footbridges, eventually throwing a 16-ton vehicle bridge across a river that the French had considered impassable under those conditions. It took them most of a day. What the record shows, when you look at it carefully, is that the German engineers at Sedan were brave, well-trained, and working to the absolute limit of what their equipment and doctrine permitted. The bridge they built was a product of determination and precise prior rehearsal, coordinated from above by officers who knew every step in the sequence. That coordination structure, which the Germans called Auftragstaktik at the tactical level, contained something in its engineering application that the American system did not share. The German pioneer officer was trusted to execute a defined mission against a defined obstacle. He was not trusted, and his organization was not designed, to solve problems that had not been anticipated in the mission order. When the obstacle changed, when the bank was steeper than the map showed, or the current faster than the reconnaissance had reported, the German pioneer adapted within a narrow band of available solutions. His equipment was specialized. His bridging sets were heavy, designed for deliberate crossings of known rivers after thorough preparation. His training was thorough but vertical, deep in one method rather than broad across several. The German Pioneer Battalion in the Western European theater of 1944 was organized around 4 companies, each of which had a defined specialty. Bridging companies carried the Schwer Pionierbruck, the heavy engineer bridge, a boat bridge designed for crossings of major rivers in conditions where the Army controlled both banks, or at least had suppressed the far banks sufficiently for deliberate work. The assault company was trained for breaching and demolition. The two rarely operated in combination below the battalion level, and the battalion was held at division or corps, not assigned permanently to the leading infantry regiments. This was a reasonable organizational decision for an army conducting the kind of mobile offensive operations the Wehrmacht had been conducting from 1939 to 1942. It was a less reasonable decision for an army conducting a defense of fixed lines against an enemy who was going to probe those lines at multiple points simultaneously with the intention of finding the one that gave way. The pioneers got to the breach after the infantry reported it, which in practice meant the breach had already been exploited before the pioneers arrived to seal it. The American combat engineer of 1944 had been built on a different proposition. The engineer school at Fort Belvoir, Virginia, and the training programs that radiated out from it through the 1930s had started from the assumption that the American Army would fight its next war in places and conditions that no one had fully mapped. The rivers would be wrong. The roads would be wrong. The demolitions the retreating enemy left behind would be creative and unpredictable. The American engineer had to be a generalist, trained in assault river crossings, in road and airfield construction, in the breaching of minefields and obstacles, in demolitions both offensive and defensive. He had to be able to improvise with local materials when his own ran out. He had to do all of this under fire, because the American doctrine placed engineers forward, not behind, attached to the leading infantry, rather than held back at division level until the situation was stabilized. This was not a casual decision. It was the product of a specific institutional argument that had been running inside the Army Corps of Engineers since at least 1926, when a study group at Fort Belvoir produced a report on the lessons of the Western Front that concluded, with some bluntness, that the engineers who arrived after the battle were too late. The battle was won or lost at the obstacle, not beyond it. The engineers had to be at the obstacle when the infantry arrived, not waiting on the road behind. What this produced by 1944 was a force that the German army simply had no template for. The 1st Engineer Special Brigade at Omaha Beach on June 6th was not supposed to be the primary combat arm on that beach. The plan had called for the engineers to breach the beach obstacles under cover of the assault infantry's fire. The plan met the beach and ceased to function. What happened instead is documented in the after-action report of the 299th Engineer Combat Battalion, which reads in places less like a military document than a list of names attached to specific act performed under specific fire. Staff Sergeant William Ogden, landing with the first wave at Easy Red Sector, found his boat taking fire before the ramp dropped. He led his demolition team across open beach to the first belt of obstacles and began clearing them, while German machine guns on the bluffs fired down the beach at approximately knee height. The report records that Ogden's team cleared a 50-yard gap in the first obstacle belt before a mortar round killed 2 of his men and wounded a 3rd. He continued clearing with the men he had left. The engineers that morning breached 16 gaps in the beach obstacle belt. The official Army history records that without those gaps the infantry could not have cleared the beach, and the follow-on waves would have piled up on top of the first, still taking fire. The infantry that crossed those gaps went on to clear the bluffs. The engineers who opened them are, in most tellings of Omaha Beach, mentioned briefly and then moved past. The operational history does not pause long on them. The gaps were open. The story moves on. The casualty count for the engineer battalions at Omaha tells its own story. The 299th Engineer Combat Battalion lost 31% of its strength in the first 2 hours. The 146th Engineer Combat Battalion lost 40%. These were not support troops caught in a fight they had not expected. They were the first wave, working alongside the first wave infantry with their demolition charges and their wire cutters and their systematic knowledge of how to breach the obstacles the German engineers had spent months laying. The German beach defense plan had accounted for the infantry, the tanks, the naval gunfire. It had not fully accounted for what happened when the men whose job was to clear the obstacles kept clearing them regardless of the fire coming down the beach. That elision is part of what makes the prisoner accounts so striking. The German officers who described what they saw from the far side of the wire were describing exactly what the operational histories moved past. They were describing the appearance of capability where none had existed. The crater that was filled before morning. The bridge that was not there at dusk and was carrying vehicles by midnight. The minefield that had stopped American infantry for 2 hours and then, without any visible reason from the German side, stopped stopping them. The mine problem deserves its own accounting, because it was one of the places where German tactical confidence was highest and where the American engineering response most directly contradicted German calculations. The German S-mine, the shrapnel mine 35, was the most feared anti-personnel device in the Western European theater. It was a bounding fragmentation mine, triggered by pressure or a tripwire, that launched a steel cylinder to waist height before detonating and scattering over 300 steel balls in a 20-yard radius. German engineers had laid them by the millions along the Atlantic Wall and in the fields and lanes of Normandy and the Rhineland. The Wehrmacht's own studies estimated that a well-laid minefield could slow an attacking infantry company to roughly 1/5 of its normal rate of advance. Against an enemy that relied on trained sappers using manual probes to clear one mine at a time, that estimate was accurate. The American answer was not primarily a better probe. The American answer was the M1A1 mine detector, the Polish-designed Kosaki mine detector adopted and mass-produced from 1942 onward, combined with a doctrinal decision that changed what mine clearing looked like at the squad level. American infantry squads in Normandy were trained to include mine clearing as a standard task, not a specialist function called forward from a separate unit. Every squad leader carried the information. Every platoon had men trained to probe and mark. The dedicated engineer mine clearing teams worked alongside infantry, not sequentially behind them. The German prisoner reports from the Normandy fighting describe their confusion about this at some length. A sergeant of the 352nd Infantry Division, captured near Isigny in late June and questioned by 1st Army G2, said that the Americans appeared to walk through the minefields the way the German pioneers had been trained to probe through them, carefully but without pausing the advance. He said his company had relied on the minefield east of their position to delay any American approach long enough for their mortars to be brought to bear. The American infantry came through the minefield before the mortars had completed ranging. He described this as being hit by something that was not supposed to reach you yet. The Siegfried Line, the West Wall, was where the German engineers had done their most thorough work and where the American engineering response reached what many of the post-war Army histories called its operational maturity. The line ran from the Dutch border to Switzerland, roughly 390 miles of concrete pillboxes, anti-tank obstacles known as Dragon's Teeth, interlocking machine gun positions, and wire and mine belts designed to break any frontal assault and hold it long enough for mobile reserves to counterattack. The German army had been building and improving it since 1938. It was, by any measurement the record supports, a formidable defensive system. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. The first U.S. Army's crossing of the Siegfried Line in the autumn of 1944 was not a single elegant operation. It was a grinding, expensive, piece-by-piece assault that took weeks and cost thousands of casualties. The German defenders were skilled, tenacious, and fighting on ground they had prepared for years. What the after-action reports and the prisoner interrogations both document, with unusual agreement from opposite sides, is the specific thing that made the assault succeed where earlier calculations had suggested it might not. The engineers got the infantry through the Dragon's Teeth. The anti-tank obstacles of the West Wall were rows of reinforced concrete pyramids, each roughly 3 to 5 feet tall, set in staggered rows deep enough to stop any tank and channel infantry into kill zones covered by fixed machine gun positions. They had been designed by engineers who knew exactly what American armor would attempt and had prepared the ground accordingly. The American response, which the German defenders saw developing across the wire in the first days of October, was not what the West Wall's designers had anticipated. The engineers brought up M1 tank Dozer blades, M4 Sherman tanks with bulldozer attachments that had been field-modified and later factory-produced after the Normandy bocage fighting had demonstrated their value. They also brought Composition C2 demolition charges, which the engineer companies used to crack the concrete at the base of the teeth, so the dozers could push the broken sections aside. The combination was slow. It was expensive in men and machines. The German fire was heavy throughout, and it worked. The dozer tanks came out of an observation made by Captain John Wozencraft of the 238th Engineer Combat Battalion during the bocage fighting in July, when he watched Sherman tanks unable to breach the earthen hedgerow banks because their hulls rose dangerously over the crest and exposed their belly armor to German fire. Wozencraft began experimenting with steel prongs welded to Sherman bow plates, cut from the Belgian Gate Beach obstacles the engineers were clearing at Omaha. The improvised devices, tested first by Sergeant Curtis Cullen of the 102nd Cavalry Reconnaissance Squadron, who has sometimes been given primary credit for the design, allowed tanks to push through hedgerow banks at ground level. General Omar Bradley saw a demonstration in late July and ordered the modification applied to 3 out of every 5 Shermans in the First Army before the breakout. That sequence, observation in the field, improvised solution, rapid mass application, is the signature of the American engineering effort throughout the campaign in a way that the German prisoner accounts keep circling back to without being able to fully name. What the captured German officers saw and could not fit inside their operational vocabulary was an army that treated engineering problems as engineering problems rather than as exceptions to be escalated. The American engineer sergeant at the hedgerow was permitted to try the steel prongs. The American engineer captain was permitted to recommend their mass adoption. The chain from observation to implementation ran in weeks rather than months. The armored Dozer itself had a parallel story in the Pacific Theater, where engineers of the Naval Construction Battalions, the Seabees, had been building airfields on coral and volcanic rock under fire since 1942. The Seabees were a different organization from the Army Combat Engineers and Structure and Service Branch, but they had been built on the same philosophical proposition: that construction was a combat task, and that the men who performed it would be placed where the construction was needed, not held back until conditions permitted. By the time the European campaign reached its final phase, the two organizations shared an institutional vocabulary that had no precise German equivalent. The German language had words for pioneer, for sapper, for engineer. What it did not have was a word that meant construction under direct fire as a planned operational phase. The German army, to be direct about this, had its own engineering innovations during the war. The Goliath tracked mine was a sophisticated remote-controlled demolition vehicle. The Brückenlegepanzer, the bridge-laying tank, was a capable piece of equipment. The German pioneer units that built the Rhine bridges in the 1940 campaign were doing work that any military engineer would recognize as excellent. The German system was not short of capable men or creative engineers. What it was short of was the institutional bandwidth to absorb field innovation at the pace the war was moving. The testimony that runs through the prisoner records on this point is not triumphalist. The German officers who described what the American engineers were doing were not, in most cases, describing failure on their own side. They were describing a phenomenon outside their frame of reference. One Oberstleutnant of the 19th Army, taken prisoner during Operation Dragoon in southern France and interviewed at length by 7th Army intelligence officers, said that the American engineers appear to treat every obstacle as though it had already been solved, and they were simply applying the solution. His phrasing in German was more specific than the translation conveys. He was describing an attitude as much as a capability. That attitude had a supply chain behind it. The Rhine crossings of March 1945 were the engineering operation the whole European campaign had been building toward, and the documentary record of those crossings is where the full weight of the American investment in combat engineering becomes most visible. The First Army seizure of the Ludendorff Bridge at Remagen on March 7th was an accident of timing, a bridge that the German engineers had wired for demolition but had not fully detonated before the 9th Armored Division's leading elements reached it. What happened afterward was not an accident. Within 24 hours of the capture, the 9th Armored Division engineers and the 291st Engineer Combat Battalion were working on the badly damaged structure while German artillery, aircraft, and V-2 rockets attempted to destroy it. They kept it standing long enough to pass 25,000 men across. When the bridge finally collapsed on March 17th, having held for 10 days beyond any engineering calculation of its remaining load capacity, the Army had already thrown 2 tactical floating bridges across the river alongside it and was working on a third. The Treadway Bridge, the M2 steel floating bridge that became the standard American tactical river crossing system from 1943 onward, is worth examining because it represents the kind of unglamorous logistical investment that wins campaigns without ever appearing in the headlines. The M2 Treadway was a pneumatic float bridge, its buoyancy provided by rubber pontoons, and its deck by interlocking steel treadway panels that could support a 30-ton load, enough for a Sherman tank. It was designed to be assembled by a 60-man engineer company in 4 to 6 hours, faster in practiced hands. Each bay of the bridge was pre-fitted so that 2 men who had practiced the sequence could lock it to the next bay in the dark, in rain, in current, by feel, if necessary. The Army's engineer training programs at Fort Belvoir ran Treadway assembly exercises at night as a matter of course from 1942 onward, on the premise that the rivers that needed crossing in combat would be crossed at night, when German observation and direct fire were degraded. By the time the Rhine crossings began, the Treadway companies of the American Army had crossed so many rivers, under so many different conditions, that the official time estimates had become conservative. At the Rhine near Wesel on March 24th, the 17th Airborne Division's supporting engineers completed a Treadway bridge capable of bearing armored vehicles in 10 hours under sporadic artillery fire. The German engineers watching from the far bank during the Moselle crossings, the Roer crossings, and finally the Rhine crossings were watching a capability that had been purchased over years of institutional investment, field innovation, and the kind of mass production that only an economy the size of America's could sustain. The United States manufactured over 400,000 bridging bays during the war. Germany manufactured far fewer, and German production priorities, concentrated on armor, aircraft, and submarine construction, never allocated resources to bridging material at the scale the American Army was consuming it. A captured German engineer officer at the Rhine told his interrogators that the speed of the American bridge laying was, from the German side of the river, simply a matter of watching until it was done. There was no point in the process where it looked like it might stop. The men kept working. The bridge kept growing. That observation carries something in it that goes beyond tactical analysis. The men kept working. The engineer who stayed at the obstacle when the rifle companies had gone aground, who kept clearing mines while mortar fire was still walking across the clearing, who drove the Dozer tank into the dragon's teeth one more time after the first pass had stalled, was not doing something that can be fully explained by doctrine or equipment or the supply of treadway panels. The 291st Engineer Combat Battalion's actions at Remagen, the 299th's record on Omaha Beach, the 10th Combat Engineer Battalion's crossing of the Moselle under fire at Dornat. These appear in the records as operational results. The men behind them appear as names in casualty lists and citation registers that most military histories do not pause on. The Bronze Stars and Silver Stars awarded to combat engineers during the European campaign occupy hundreds of pages of the official record. The citations describe, in the Army's clipped formal language, specific acts at specific locations on specific dates. They describe men who cleared minefields while under direct fire because the infantry behind them could not move until the field was clear. Men who paddled assault boats across rivers to recover wounded soldiers after the initial crossing had been thrown back. Men who worked on bridges that were taking artillery fire because the bridge was needed and the fire was the condition of the work, not a reason to stop it. The German prisoner accounts, taken as a whole, describe something that the citations and the operational histories both point toward from different directions. They describe an army that had decided, at the level of doctrine and training and equipment procurement, that engineering was a combat task and that the men who performed it would be trained and equipped and placed accordingly. The German army had made a different decision, not a wrong decision for all purposes, but a different one. The German pioneer was a specialist, a craftsman of specific obstacles and specific solutions. The American combat engineer was a generalist forward, a man whose job description began with the phrase "under fire" and proceeded from there. The crossroads at Dornat on the Moselle, the gap in the dragon's teeth at the West Wall, the Treadway Bridge at the Rhine. These are the places where what the prisoner interrogations were describing became, for a few hours, physically visible. An obstacle was there, and then, by the work of specific men whose names are in the records for anyone who goes looking, it was not there anymore. The German officer in his command post watching the American side of the river through binoculars could not find a word in his tactical vocabulary for what he was seeing. The bridge was appearing. The field was being cleared. The crater was being filled. The American army was advancing not because the obstacle had been removed from the plan, but because the men assigned to remove it had removed it. The last crossing of the Moselle at Dornat was completed in the early morning hours of the day after the engineers arrived. The 10th Combat Engineer Battalion lost 11 men building it. The crossing it supported put 2 regiments of the 3rd Infantry Division on the east bank with their vehicles and weapons, from which position they broke the German main line of resistance in that sector within 48 hours. The bridge is gone now. The river runs where it ran then. The farm fields on both banks grow what they grew before the war and after it. The men who built the bridge under fire in the dark are in the records of the National Archives and in the histories of their units, which were written by men who served in them and then spent the rest of their lives making sure what happened was written down somewhere. That is where this story ends. At the record, the German prisoners could not explain what they were seeing because the frame they had been trained to see through did not contain it. The American combat engineer in 1944 was not simply a soldier who could also build things. He was the product of a 20-year institutional decision to treat obstacles as problems to be solved at the point of contact, with the tools available by the men present in the time the operation allowed. The Germans built the best defensive obstacles they knew how to build. The Americans trained men to go through them. The record shows who was right about what that required. Thank you for staying with us until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.